In this lecture, we look at thermodynamics. Thermodynamics looks at the internal energy of systems. A key characteristic, or quantity in thermodynamics, is temperature. Temperature is a fundamental SI quantity, and it's given in terms of Kelvin, or symbolized by the letter K. So degrees of Kelvin or degrees K. Temperature not only looks at the internal energy of a system, but also deals with the material characteristics of the system. So temperature is not a measure of the energy of the system alone, but a combination of the material characteristics of the system as well as the internal energy of the system. For example, let's say we have this system here, which consists of two blocks that have been in contact for a long time, so they are at the same temperature. Then we separate the two. Well, whatever energy was in the big block has to be larger than the energy that was in the small one because it's a larger system. This is what I mean by they were the same temperature. Temperature does not only talk about the internal energy system, but it has to do with the material or physical characteristics of the system, so that the small block has less energy than the large one. Similarly, the same mass of water holds more energy than the same mass of copper at the same temperature, simply because of the material characteristics of water. We will see that water has a greater capacity for heat than copper. The Zeroth Law of Thermodynamics, perhaps you're wondering why we start out with the Zeroth Law rather than the first law. Well, the first law was discovered first, but then they said maybe we should have something before that, and that's how we came up with the Zeroth Law of Thermodynamics. If objects A and B are in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. Or maybe in other words that are easier to understand, objects that are in thermal equilibrium have the same temperature. Separate objects with the same temperature that are placed in contact do not change thermally, i.e. they are in thermal equilibrium. So let's look at temperature more closely. The Kelvin scale of temperature has two fixed points. The first is 0 degrees Kelvin, and that's taken to be the absolute minimum temperature. The second is 273.16 Kelvin, and it is the temperature of the triple point of water, the point where ice, water, and vapor coexist at 1 atmosphere of pressure. Let's look at an example of thermal equilibrium. Let's take two water baths that have the same internal energy. The first bath is 10 times larger than the second bath. Are they in thermal equilibrium? And which bath has the higher temperature? For baths to be in thermal equilibrium, they have to be at the same temperature, not at the same internal energy. So if we go back to our system from the previous page, that were at the same temperature, and then we separate them, we found in this case that the energy of the small block was much less than the energy of the large block. Now let's take a look at these two systems, but now consider say that they're at the same internal energy, so E small is equal to E large. Well, if we want to get back to the same temperature in thermal equilibrium, then we have to have a case where the small system on the left is much smaller than the energy of the large system on the right. So we have to add some energy to E large to make it much bigger than E small. So you need to add energy to the large bath to bring it into thermal equilibrium with the small bath so that T small is, the temperature of the small system is much higher.